So let's look at the trend in ionic radius. So this is going to be the size of ions versus just atoms. As you go down a group, okay, we're looking at the group trend. As you go down a group, ionic radius increases, and for the exact same reasons as it did with the atomic radius. So if you look at the alkali metal ions, okay, Li plus, Na plus, K plus, and Rb plus, you'll see that as you go down, they get larger. Now the periodic trend, the same as the atomic radius, the ionic radius is going to decrease, again, for the same exact reasons. That's your periodic trend. Okay, but if you look, you'll notice that the cations, as they go across, they get smaller, but then the anions all of a sudden get bigger, and then they get smaller as they go across. So this is a little bit more complicated than the atoms. So let's look at cations and anions and compare them to their atoms. So first of all, cations are always smaller than the atom that they came from. For instance, Na plus is smaller than Na. Well, let's look at why. If you look at the electron configuration for Na, 1s2, 2s2, 2p6, 3s2, when we talked about how metals form ions, cations, we said that they're going to lose their valence electrons. So sodium ion is going to have an electron configuration of 1s2, 2s2, 2p6. So if you look, sodium has 3 energy levels, okay, and sodium ion has only 2 energy levels. So it makes sense 3 energy levels would be bigger than 2 energy levels. So sodium is bigger than sodium ion. Also, Na plus has the same number of protons as Na, okay, pulling more effectively on fewer electrons. Okay, so sodium and sodium ion both have the exact same number of protons, right? They have 11 protons, that's the atomic number. But in the case of sodium, those 11 protons are trying to pull on 11 electrons. And for sodium ion, they have to only pull on 10 electrons, so they're able to pull them closer. Okay, so cations are always smaller than their atom. Okay, well, anions are always bigger than their atom. So let's look at fluoride versus fluorine. Fluorine is 1s2, 2s2, 2p5. Remember, we talked about how anions form by filling out this energy level. Okay, so it's going to need another electron. So it's going to be 1s2, 2s2, 2p6. Right? It's going to want to become isoelectronic with neon. So why is fluorine bigger then? Well, it's not about energy levels, right? Because they have the same number of energy levels. So we can't use that as a reason. Okay, instead, we say that fluoride has the same number of protons, pulling less efficiently, right? Less effectively on more electrons. Okay. Again, fluorine, okay, if you look at the periodic table, has 9 protons. 9 protons. Fluorine and fluoride both have 9 protons. Okay, 9 electrons, but here 10 electrons. So in the case of fluoride, the 9 protons are trying to pull on more electrons, and they aren't able to pull them as close. So fluoride is bigger than fluorine. F minus is bigger than F. Okay. Also, a second reason is electrons repel, right? And now fluoride has more electrons, so they repel more, so fluoride's a little bigger. Okay, so there's a couple reasons why fluoride is bigger than fluorine. Look again, what happens is, simple enough, when you go down, ions get bigger. Okay, it doesn't matter if they're cations or anions, they get bigger. Cations, the metals, they decrease in size as they go across. And then the anions decrease in size as they go across. But anions, right, are bigger than cations. So they get smaller in two groups. The cations, the positive ions start pretty small and get smaller. The anions start pretty big and get smaller. Okay? So that's kind of an overview of ionic radius.